The Earth-Moon system represents one of the most remarkable planetary satellite relationships in our solar system, characterized by unique properties and complex interactions that have shaped the evolution of both bodies. The Moon is Earth's only natural satellite, orbiting at an average distance of 384,399 km, 238,154 meters, roughly 30 times Earth's diameter. This celestial partnership is distinguished by the Moon's relatively large size compared to its parent planet, with a diameter about 1/4 that of Earth, approximately 3,474 kilometers, making it the largest natural satellite relative to its primary planet in the solar system. This special relationship has profound implications for Earth's environment, from governing ocean tides to influencing our planet's rotational stability, creating conditions that have been critical for the development of life on Earth. The prevailing scientific theory for the formation of the Earth-Moon system is the giant impact hypothesis. According to this model, approximately 4.51 billion years ago, not long after Earth's formation, a Mars-sized planetary body named Theia collided with the proto-Earth in an oblique impact. This cataclysmic event ejected a tremendous amount of material into orbit around Earth, beyond our planet's Roche limit of approximately 2.56 Earth radii, which subsequently accreted to form the Moon. Computer simulations of such impacts have produced results consistent with the mass of the lunar core and the angular momentum of the Earth-Moon system, lending strong support to this hypothesis. Isotope dating of lunar samples suggests the Moon formed around 50 million years after the origin of the solar system. What makes the giant impact theory particularly compelling is that it explains several observations that alternative formation theories cannot adequately address. Most notably, Earth and the Moon share nearly identical oxygen and tungsten isotopic compositions, unlike other inner solar system bodies such as Mars and Vesta. This isotopic similarity suggests thorough mixing of material from both bodies during formation, consistent with the vaporization and subsequent condensation following a giant impact. Alternative theories such as fission, gravitational capture, or co-formation fail to account for the high angular momentum of the Earth-Moon system or other observed characteristics. The Earth-Moon system operates around a common center of mass, or barycenter, located approximately 1,700 kilometers beneath Earth's surface, about a quarter of Earth's radius. This arrangement means that rather than the Moon simply orbiting Earth, both bodies effectively orbit this shared gravitational focal point, with Earth making small counterbalancing movements. The Moon itself is a differentiated body with distinct geophysical layers, a crust averaging about 50 kilometers in thickness, a mafic mantle more iron-rich than Earth's, and a partially molten core region with a solid inner core approximately 240 kilometers in radius. In mass terms, the Moon constitutes about 1.2% of Earth's mass, making it the fifth largest natural satellite in the solar system. Its surface gravity is approximately 1/6 of Earth's, 0.1654 g, giving it the second highest surface gravity among all moons in the solar system, after Jupiter's moon Io. The Moon's substantial size relative to Earth creates significant gravitational interactions that influence both bodies in complex ways, from raising tides to affecting rotational dynamics over geological timescales. The Moon's orbit around Earth follows a slightly elliptical path with an orbital eccentricity of 0.055. It completes a full orbit with respect to the fixed stars, its sidereal period, in approximately 27.3 days. However, because the Earth-Moon system simultaneously orbits the Sun, it takes slightly longer, 29.5 days, for the Moon to return to the same phase as viewed from Earth. This longer period, known as the synodic month, determines the lunar month and the familiar cycle of lunar phases. One of the most distinctive features of the Earth-Moon relationship is tidal locking. The Moon has achieved a 1.1 spin-orbit resonance, meaning its rotation period exactly matches its orbital period around Earth. This synchronization explains why we only see one side of the Moon, its near side, from Earth. Despite perfect tidal locking, lunar libration, a slight wobbling effect, allows observers on Earth to see approximately 59% of the Moon's surface over time, rather than exactly 50%. Unlike most planetary satellites whose orbital planes closely align with their planet's equatorial plane, the Moon's orbital plane is more closely aligned with the ecliptic plane, Earth's orbital plane around the Sun. The gravitational attraction between Earth and Moon manifests in numerous observable phenomena, most notably Earth's ocean tides. These tides occur because the Moon's gravitational pull is slightly stronger on the side of Earth facing the Moon and slightly weaker on the opposite side, creating a differential force that stretches Earth along the Earth-Moon axis. As Earth rotates through these gravitational gradients, coastal areas experience the regular rise and fall of tidal waters. Beyond ocean tides, both planetary bodies experience solid body tides. The lunar crust undergoes tides of approximately 10 centimeters amplitude over a 27-day cycle. The cumulative stress from these tidal forces produces moonquakes, which, though weaker than typical earthquakes, can last significantly longer, up to an hour, due to the dry, fragmented nature of the lunar crust that efficiently scatters seismic vibrations. Recent research suggests that the Moon's gravitational influence may also contribute to maintaining Earth's magnetic field, highlighting another dimension of this celestial partnership. The Earth-Moon system is not static but dynamically evolving due to continuous tidal interactions. The slight delay in Earth's tidal bulges creates a torque opposing Earth's rotation through a process known as tidal acceleration. This mechanism transfers angular momentum from Earth's rotation to the Moon's orbit, simultaneously slowing Earth's rotation and pushing the Moon into a higher orbit. Laser ranging experiments using reflectors placed on the lunar surface during the Apollo missions have precisely measured this recession, finding that the Moon moves away from Earth at approximately 38 millimeters per year. Correspondingly, atomic clock measurements reveal that Earth's day lengthens by about 17 microseconds annually. This tidal evolution has profound long-term implications. Theoretically, in approximately 50 billion years, Earth's rotation would slow until its day matched the Moon's orbital period, resulting in Earth becoming tidally locked to the Moon, just as the Moon is currently locked to Earth. However, the Sun's evolution into a red giant phase will likely engulf or severely disrupt the Earth-Moon system long before this endpoint is reached. Should the system somehow survive this phase, solar atmospheric drag would eventually cause the Moon's orbit to decay until it crossed Earth's Roche limit at approximately 18,470 kilometers, at which point tidal forces would disintegrate the Moon into a ring system that would mostly impact Earth. The Moon's surface bears testimony to its 4.5 billion year shared history with Earth. Its most extensive topographic feature is the far-side South Pole Aitken Basin, approximately 2,240 kilometers in diameter, the largest crater on the Moon and the second largest confirmed impact crater in the solar system. The Moon's dark, relatively featureless plains called Maria, Latin for seas, are vast, solidified pools of ancient basaltic lava that erupted primarily into impact basin depressions. These distinctive features, along with thousands of smaller craters, rills, and mountains, chronicle a violent history of impacts that affected both Earth and Moon during the early solar system. Recent discoveries have revealed intriguing features, such as a confirmed cave near the Sea of Tranquility, identified as an entry point to a collapsed lava tube approximately 45 meters wide and up to 80 meters long. With a stable temperature of around 17 degrees Celsius, such features could potentially provide hospitable environments for future human lunar activities, offering protection from extreme temperatures, solar radiation, and micrometeorites. The Earth-Moon system represents a remarkable planetary partnership that has significantly influenced the development of our planet and potentially enabled the emergence of complex life. From moderating Earth's axial tilt to controlling ocean tides, the Moon has played an integral role in Earth's environmental stability. As humanity contemplates establishing a permanent presence on the Moon, understanding this unique relationship deepens our appreciation of the dynamic forces that have shaped our cosmic neighborhood over billions of years.